Good morning, guys of grade 8. Today, inshallah, we're going to start on lesson 2 of chapter 19. So, we're going to talk about the electric current and simple circuits. So, in the first lesson, we already studied the static electricity, and we said that it's accumulation of a charge on a surface of an object. Once this charge does not flow, so we call this a static charge or static electricity. And then we studied how object could be charged, whatever by contact or conduction or induction. Today we're going to talk about the other type of electricity, which is the electric current. Okay, and we are going to know what are the electric circuits. So by the end of this lesson, we should be able to know or to answer the following questions: What is the relationship between electric charge and electric current? What are voltage, current, and resistance, and how they do affect each other, okay, in what is known as Ohm's law. So then here the new vocabulary which we're gonna learn, okay, electric current, electric circuit, electric resistance, voltage, Ohm's law. So let's start here in the beginning. So last time, as we said that once electrons are already donated from one substance to another, that's the substance which give the electrons will be positively charged, and the one which gonna receive the electrons or the electrons will be on that surface is gonna be negatively charged, and in that case we call this static electricity. But once this electron is found a way to flow or to move from one point to another, in that case, it's not static anymore. It's in that case we call this a current. Okay, so what is a current? Actually, current is the flow of electric charge. That means the flow of electrons. So once electrons find a way to flow to pass within a substance, of course, okay, we call this electric current. And of course, the substance which allow electron to pass through is a conductor. So like this, we talk about metals for approximately or that as we know all metals are conductors. Some other substances could be also conductors. Okay, so whatever, once the electrons find, okay, or found its way to flow or to pass from one point to another, that's form electric current, and it is no more static electricity. So like this, we have the first definition here: electric current. What is electric current? Say that the movement of electric charge. Okay, then here we pause. So actually, electrons to keep flowing, okay, it must move within a complete or closed path. That means if you have a piece of wire like this, okay, for example, that's fine. Look at me. If I have a piece of wire like this, it's a metal, okay, metal of copper or something like this, then I connect it with a battery. The signs mean the battery. Okay, so like this, could electrons pass from the battery or could electrons pass within the wire? Actually not. Why? Because that doesn't represent a complete path. Okay, in that case here, electrons will not flow. So electrons to flow or to form an electric current, we must have electric circuit. So what is electric circuit? A closed or complete path in which electrons travel. So like this, okay, for example, if I have this battery and I connect this bulb, okay, like that, and then I close the circuit, now electrons could flow. So we're gonna find that electrons now could move within this. So it has a closed path to move in. So the electrons keep moving from the negative pole of the barrier to the positive pole. And we must have a device or we must have something we could load, okay, that is going to change the electric energy into another form of energy. That the purpose of all electric circuits. So all electric circuits, they have one thing in common, that they transfer the electric energy into another form of energy. And it's too dangerous if we just connect the negative pole of a battery to the positive pole of the battery, because that may cause the battery to explode. Okay, so of course that is not right. What's the purpose or what the benefit that I connect the negative to the positive? Okay, if I gonna have a form or as a form of energy. So the circuit here, as we said, must contain a load or device that convert the electric energy into another form of energy that we need. So like this, that represent an electric circuit. Okay, it's a complete closed path. Okay, that allow electrons to flow. So like this flow or movement of electrons, we call this the electric current. So here, as we said, that's why all electric circuits have one thing in common, that they transfer the electric energy into another form of energy. So here we have a point. Electrons flow in a wire, so they make a current. Do all energy or electric sources, that means do all batteries, okay, or do all generators or whatever that create electricity, they produce the same current? Okay, so that's a big question. Of course not. Not all of them produce the same current. Some of them they produce powerful current, are more powerful current rather than other currents. So that means the currents already have a kind of strength, or I could measure the current. So how we could measure the current, or how we could find the power of the current? So we said that actually the current could simply measured, or the amount of the current is could simply measured, okay, by how many electrons or how many charges are flowing. So whatever the amount of electrons that are flowing, okay, from the battery or from the electric source within the electric circuit, the amount of electrons that already passed out from the electric source, okay, they will move in this complete circuit and return back to the electric source. And actually, or we just need here to give you a hint or an idea that actually the battery doesn't produce electrons. A battery produces kind of energy, that the electric energy, which allow or pushes, okay, the electrons of the wire, and then the electrons of the wire gonna push the next electron, and the next electron push the next, and so on until, okay, the energy return back to the battery, and keep doing like this, okay. This energy actually in the battery is produced due to a chemical reaction that's happening inside the battery. So once the chemical reaction is completely done, the battery run off, and it cannot, or the battery will not give electricity anymore. Okay, so like that here we get the idea. Okay, so here how electricity flow in a circuit. And of course, as you can see here, electrons to pass, we said it must have a complete closed circuit, okay? So if the circuit is open, or there is a gap in the circuit, of course, that current will not flow, or electrons will not move, because as we said, energy pushes the electrons, okay? And each electron push the next. So once we have a gap here, so the energy cannot flow, okay? In that case, okay, no electricity. So here we said that again. As we said, the electric current could be measured by the amount of electrons that flow at a certain point, or flow in a circuit, okay, in 1 second. The amount of electrons that pass is measured in a unit, we call it coulomb, okay. So like this, we could find, or we can say that electric current, okay, or we just have a new rule here, okay. What is our rule? That we said electric current, we give it a letter I. So I means electric current or current intensity, okay, equal the amount of electrons, okay, the quantity of electrons, Q, over the time, which is T. So that's electric current, okay. So the current equal the quantity, or the amount of electrons that flow past point within a second, or a certain time. So the measuring unit of the quantity of electrons, or the amount of electrons, is coulomb. So we measure the amount of electron by coulomb, and the time, of course, is measured by second. So like this, we can say that the measuring unit of current, or current intensity, is the coulomb over second. In another way, we said coulomb over second equal an SI unit. We call it ampere. We call it ampere, and we give a letter A. So ampere is SI unit of measuring the electric current or current intensity. That means how much power, or how much powerful the current is, which means how many electrons are flowing within a certain point in a certain time. So gain current equal the quantity of electrons divided by time, so coulomb over second, that equal ampere. Okay, so like this, when we said that an electric current equal 1 ampere, it means that there is 1 coulomb of electrons passed by a certain point in 1 second. Okay, so here like this, okay guys, we know what is current, and we know how current could be measured. So we see that 1 ampere of current, okay, equals about 1 coulomb of electrons flowing past a point in a circuit every 1 second, or every second. So here like this, we know what is the current. Now we pass to another point, which is the electric resistance. What is the electric resistance? So first, all we call that electric resistance, it represents the measure of how difficult, or how the opposition that the electrons face once they try to pass within a conductor, or in a circuit. That means not all materials allow the electrons to flow with the same speed, because some materials actually have different density than others. Some, okay, they have hard, or the electrons hardly to pass through them, while others easy to pass through them. So they represent here how much difficult electrons flow, or the opposition that the electrons will face while it's running within a conductor. We call this the electric resistance. So the unit of electric resistance, or we measure the electric resistance in a unit, we call it ohm, and that is the sign of the ohm. Okay. So for example, here you could find that copper resistance equals 0.004 ohms, okay, while the gold is 0.006 okay, ohms, and so on. So like this, simply you could find that the copper has the lowest resistance ever, which make the electrons pass easily through them. So like that, okay, the copper is the best electric conductor ever, and that's why it's used in making wires. As you can see, metals, okay, they have also low resistance, okay, so they could use also as conductors. While non-metals like carbon, okay, its resistance is 8.9. It's a big resistance, okay. So that means it's difficult for electrons to pass within carbon. So that is an insulator or not good or not a good conductor of electricity. For example, the best insulator ever is rubber. As you can see, you cannot read even this number, okay. The rubber has a huge resistance, which actually does not allow electrons to flow at all. So that's why we use rubber to make the handles of the screwdrivers, okay? And we use it, okay, for many purposes, okay, like the cover of the electric wires and cables and so on. So that's to prevent the electric shock or to protect ourselves, okay, from the electricity. Here we said that the cool electric conductor has a high electric resistance, and in that case, okay, that means the atoms of this material hold the electrons tightly and they prevent them to move easily or flow easily. So like this, electrons cannot pass or the current cannot pass. While you find that here the other material or the conductors, they could easily allow electrons to flow. We find also that electric resistance depends on the two factors, the length and the thickness of the material. That means two pieces of copper, okay, both the are copper posts have the same resistance, but if they are different in length and different in thickness, actually they are gonna be or they have different resistance. So let's see how that. So for example, if I have these two pieces of copper, okay, one they both have the same thickness, but one is a little bit longer or one is longer. Let's make it like this, okay. So that's A and that's B. Both are pieces of copper. A is longer than B. So once electron try to flow in A, of course, it will find a lot of opposition as it's a longer distance, okay? So in that case, okay, it will be hardly for electrons to pass, while here, because it's a short distance, electrons could pass more easily than A. So in that case, here we find as the length of the conductor increases, okay, its resistance increases. So as length increases, okay, so as length increases, also the resistance increases, okay, so it's a direct relation. While the opposite in case of thickness, okay, for example, if I have this piece of conductor, okay, and that's piece of conductor, both, okay, they have the same length, but they are different thickness, okay. So in that case, as we have larger, okay, or the thickness is more, that means we have somehow more spaces between particles, which allow the electrons to pass easily through them. So like this, we could find as the thickness or the width, okay, so thickness increases, as thickness increases, the resistance will decreases. Okay, so that's here an inversal relation. Always remember this, that if you are drinking a juice, so which one could provide you with more juice, the thick chalumeau or the thick straw or the thin one? Of course the thick one, okay, because it's allow a lot of juice to pass easily. So here like this, okay, the thick wire or the thick conductor allow electrons to move easily, so that means it has a less resistance. We're gonna stop at this point, guys. Please study this part very well from your textbook, and if you have any question, you can ask me next time. Thank you and goodbye.